So good morning, my dear students, and welcome to today's lecture. We are still in the chapter of work by energy. This is lecture number 26. Probably I'll start numbering these lectures not as work by energy but as circular dynamics now, because we are studying circular motion. Once we are done with the circular motion, we would probably jump on into the part where we would be using the concept of circular motion in work by energy. We will see what type of questions come in the exam, and those are the types of question which are normally there. Uh, Question based on circular motion in work by energy are a very common questions. These are very common questions, and they normally come in the exam, whether it's NEET or probably it's JEE Main. Let's have a quick recap of what we have done up till now in circular motion. We have discussed the basic definition of all these terms that we were supposed to know in the last lecture, that is lecture number 25. We have discussed these terms in great detail. We had seen the basic terms: angular position, the position of the particle in the circular path in terms of an angle, gradients, then angular displacement, change in angular position. Small angular displacement is a vector quantity. Large angular displacement is a scalar quantity. What type of vectors these are? Remember, these are actual vectors. The direction is given in terms of axis. Then we had seen angular velocity, two different headings. Average angular velocity, total angular displacement divided by total time. It's a scalar quantity. Instantaneous angular velocity, small change in angular displacement, or small change in angular position divided by small time, or it is the angular velocity at any particular instant. This is a vector, and it's an actual vector. If omega is constant, then the motion becomes simple harmonic. We had seen in simple harmonic motion, we have time periods, time taken to complete one revolution or one rotation. Then we have frequency, number of revolutions in 1 second. SI unit is hertz, frequency is 1 by t, and omega is 2 pi t, or 2 pi into f. You've done questions on that as well. Average angular acceleration, total change in angular velocity, delta omega divided by delta t. Again, it's a vector, actual vector. Instantaneous angular acceleration is angular acceleration at any particular instant. We have also seen and noted down the sign convention for circular motion, and the sign convention is pretty damn simple. Anti-clockwise rotation, something moving in the anti-clockwise sense, would be taken as positive. Something moving in the clockwise sense would be taken as negative. Do we all agree on this? Can I have some raised hand that we remember this? So far, so good, so clear. We discussed these things in the last class. Let us now move ahead, and I hope I have told you in the previous class what we are going to do in the next class. Yes or no? I had asked you to note down the equations of motions. Have you done that? I hope you have done it. Did you remember the homework that I gave you? Well, if you have not done it, don't worry. We will take it up in today's class. Motion with constant angular acceleration. Now, what do you mean by constant angular acceleration? Could anyone tell me what is this constant angular acceleration? What do you mean by constant angular acceleration? Remember, everything that we are doing here has already been covered has already been covered in your first chapter. In your first chapter, we have done this already. Now the heading might be looking different here than the heading there. In your first chapter, we have seen motion with constant acceleration. What happens in motion with constant acceleration? If the acceleration of the body is constant, acceleration will remain same. Here we are talking about constant angular acceleration. That means alpha. The angular acceleration is constant. That means the angular acceleration will remain same and it will never change. Do we understand this? Can I have some raise hand that we understand this, sir? Angular acceleration is same and it will not change. Now if angular acceleration is same and it does not change, your instant angular acceleration at any time alpha will be equal to your average angular acceleration between any two given point. So basically what I am going to say here is that your angular acceleration remains constant. It will not change. Now this process or this motion theoretically, not practically, theoretically is exactly similar as what we had done in the first chapter, motion with constant acceleration. There acceleration was constant, the average value of acceleration and the instantaneous value of acceleration were all same at all points. Here the angular acceleration is constant. That means the value of instantaneous angular acceleration at any given point will always be equal to the average value of angular acceleration between any two given points. Do we understand this? Can I have some raised hand that we understand this? Okay, it is pretty simple then. Now we have equations of motion in this particular case. What are the equations of motion in this particular case? Let us first try to understand the terms. The first term that you see is omega naught, which is initial angular velocity. You can call it omega 1 as well, doesn't matter. Then you have omega, which is final angular velocity. You can call it omega 2. Initial you can call it as omega 1. Final you can call it as omega 2, doesn't matter. Alpha is the constant angular acceleration. And instead of writing it as theta, let us write it as delta theta. Delta standing for change, delta theta standing for angular displacement. So these are the four quantities that would come in discussion here in this concept of constant angular acceleration. Your initial angular velocity, your final angular velocity, your angular acceleration, and your angular displacement. I'll give you a minute to note it down up till here, then I will move further ahead in the discussion. Well, I hope you have noted down the four terms. Now what we'll do is we will go through the equations of motion with constant angular acceleration, and what we will try to see here is that how are these equations exactly same, and I will repeat, exactly same as what we had done previously in chapter number 1. Now if I look at the first equation, equation number 1, equation number one says omega is equal to omega naught plus alpha t. Now can anyone tell me, looking at this equation, omega, which is the final angular velocity here, omega naught is the initial angular velocity, alpha is angular acceleration and t is definitely time. Can you tell me, have we seen this equation before? And if we have seen this equation before in a different form, what was the equation like when we had previously seen it? How was the equation looking like when we had previously seen it? Yes, Neha, that is correct. V is equal to U plus AT. That was the form in which the equation was looking there. V was final velocity, U was initial velocity, A was acceleration, and T was time. This is equation number one from your motion in 1D or motion in 2D. So now, this equation, theoretically, if you look at it, is same. Final angular velocity, initial angular velocity plus alpha t. Final velocity is equal to initial velocity plus a into t. So everything that we had done there, it is now going to come back. For example, equation number 2 was delta r, which is displacement, is ut plus half a t square. I hope, yes, yes, Neha. That was the equation, the second equation of motion that we had studied. Now, if I look at the counterpart here, the counterpart here is delta theta is equal to omega naught t plus half alpha t square. Both are same. Nothing changes. Only the terms change. Instead of displacement, we have angular displacement. In place of initial velocity, we have initial angular velocity, and in place of acceleration, we have angular acceleration. Let us now move on to the third equation. The third equation here looks like omega square final angular velocity square is equal to initial angular velocity square plus 2 times alpha into delta theta. That is equation number 3. You can very easily see, Neha, and you have already given me the answer for that one. You can easily see that this equation is same as v square is equal to u square plus 2 times acceleration into delta r, which is displacement. 3 equations done. Do we all agree on this? Can I have some raise hand? Yes, sir, we agree on this equation and no problems whatsoever. Okay. Now, if you agree on these equations, I will move on to the fourth equation. And the fourth equation, if I talk about the fourth equation in the red zone, that is the motion in one dimension wala equation, we have seen an equation where I've written V average is equal to V plus U divided by 2. Do you remember that equation? Now remember, whatever equations we are writing here, yes, Nia, very good. Whatever equations we are writing here, they're only valid for constant acceleration or constant angular acceleration. That is what you should not forget. V average, if the acceleration is constant, was V plus U divided by 2. How many of you remember this equation? Equation number 4. How many of you remember it? No one remembers it? Well, not a problem. Now, we are again revising it. So this is the time that you can remember it now. Now, if V average was V plus U divided by 2 for constant acceleration, here also we will have one equation. What would be that equation? Equation number 4 in the blue zone. What would be the equation number 4 for circular motion? How will it look like? Anyone can give me an answer. The answer is pretty damn simple. I will write it as omega average. I'm not using vectors. Why I'm not using vectors? Because instead of vectors, they are vectors. We will be using sign convention. I'll go to the sign convention once again. Let us first discuss the let us first discuss the equation. Then I will go on to the sign convention. Omega average. What will be omega average equal to? That will be simply equal to omega plus omega naught divided by 2. That would be the equation here. Am I clear with everyone? So what I'll do now here is I'll give you 2 minutes to note down equation number 1, 2, 3, 4, and then I will proceed further. So 2 minutes, note down these equations, then we will move forward. Well, I hope everyone has noted down the equation up till average velocity and average angular velocity. Now let me move on to the fifth equation, and the fifth equation would be here. Now here I will write delta theta, which is your angular displacement. Angular displacement can be written as, just add an equation here. Angular displacement is nothing but average angular velocity multiplied by t. Remember, this is a formula that we have already seen, not in this form, but in a different form. We have seen it in this way. Average angular velocity is total angular displacement divided by total time. I've just taken time on the other side. So I can write delta theta as omega average into t. Remember, this formula is always valid whether it is motion with constant angular acceleration or motion with variable angular acceleration. Delta theta is always equal to average angular velocity multiplied by time. So if I can call this equation as equation number 5, this equation becomes equation number 6. But what is peculiar about equation number 5 in all these is equation number 5 is always valid. Apart from equation number 5, all the equations are only valid if the acceleration or angular acceleration is constant. Similarly, I can write the equation number 5 and equation number 6 here. Equation number 5 here will be delta R is V average multiplied by T. Equation number 5. I'm again writing it in a dabba so that you understand that this equation is always valid, because this is the equation or this is the definition of average velocity. Average velocity is total displacement divided by total time. But here in this case, when the acceleration is constant, the average velocity or average angular velocity becomes v plus u by 2. So I can write equation number 6, delta r is v plus u by 2 times t. Am I clear with this concept, everyone? The concept of equation number 5, which is valid always, and equation number 6, which is only valid when the motion is with constant acceleration. Okay, that takes us to the last equation in this category. Last equation in this category was displacement in the nth second. And how do you find the displacement in the nth second? N can be 1 first second, N can be 2 second, third, 3 third second, fourth second, fifth second, sixth second, seventh second. In one particular second, how much is the displacement? Remember, the concept is very simple. It is the displacement in the displacement of the particle in n seconds. So if I write nth, displacement in n seconds minus displacement in n minus 1. Do we remember this, everyone? If I want to find how much the particle has displaced in the 5th second, listen to me very carefully. If I have to find out how much the particle has displaced in the fifth second, what do? I find the displacement in 5 seconds from 0 to 5. I find the displacement in 5 seconds. Then I subtract the displacement in 4 seconds. So if I subtract displacement in 5 seconds from displacement in 4 seconds, I will get displacement between 4 and 5, which is the 5th second, end of 4th, and beginning of 5. That is how you can find out the displacement in the nth second. If you put the values here, you will end up with a very simple equation of displacement in the nth second. Does anyone remember that equation of displacement in the nth second? If anyone remembers it, I would be pretty glad. What is the displacement in the nth second ka formula that we have derived? Anyone remembers it? Don't look at the formula on the left hand side, it has been typed wrongly. So I'm looking for the displacement in the nth second ka formula. Does anyone remember it? Abhiram, Neha, all the participants in the class, Kishore, Tarun, Vasant. Does anyone remember the formula for displacement in the nth second? Displacement in the nth second. Does anyone remember the formula? No one seems to recollect it. Well, not a problem if you don't recollect it. U plus A into n minus half. And this is a new way in which I'm writing this because I've seen that this is simpler to remember. U is the initial velocity, A is the acceleration, N is the second, so that, don't do this, so that why you have to do stupidity? Let me continue with this. So the formula that I was looking for was displacement in the nth second is U plus A into n minus half. U standing for the initial velocity, A standing for the constant acceleration, n standing for which second you are talking about. If you want to find it out in the 5th second, put n as 5. For 6th second, put n as 6, and so on. Now these are the formulas for the red zone motion in one dimension wale formulae. Now can we replicate the same formula here? What would be the formula for angular displacement in the nth second? So the first formula would be like this. I'll just take this off. So displacement in the angular displacement in the nth second would be angular displacement in n seconds minus angular displacement in n minus 1 second. So that would become the first formula. The first formula is pretty damn simple. It is similar. All the formulas are similar, as you can see. All the formulas are similar. Displacement, angular displacement in the nth second is angular displacement in n seconds minus angular displacement in n minus 1 second. Now, if I put the values, I will get the formula for angular displacement in the nth second. Can anyone, looking at the formula on the right hand side, tell me what will be the formula for the left hand side? Anyone? I hope I am audible and visible to all of you. Can you all see me? Can you all hear me? Okay, great. Yes, Neha. Can anyone tell me what will be the formula for angular displacement? Right hand side, the right side, the formula is there. Can you tell me what will be the formula on the left hand side? Well, I assume that it is difficult for you to write it on the screen because there are terms. Instead of omega, you can write W. Instead of alpha, you can write E. Same thing. Anyways, I will do it for you. So that will be equal to omega naught, which is initial angular velocity, plus alpha into n minus half. And this is how this formula, equation number 7, would look like. Do we all understand this? All the equations starting from equation number 1 till equation number 7. Is it clear to each and everyone? Can I have some raise hand that we understand this, sir? No problems in understanding this equation. And we have done a thorough revision of all the equations together. So it's a revision from your first chapter till whatever has been covered. Now I'll give you 2 minutes to note down all the equations. If you have any problems, any doubts, please feel free to ask me. I'll give you 2 minutes. So I hope all of you have noted this down. Now remember, apart from equation number 5, this equation, the equation in the dabba, this equation, and one more equation, this one, which is the basic concept. These two equations which are in dabba, they are all valid for constant acceleration only. Equation in dabba, these are definitions, these are concepts, and they are valid whether the acceleration is constant or the acceleration is valid. But remember, and remember it nicely, that we are dealing with vectors here. We are dealing with vectors here. Now vectors, now what we are writing here are magnitudes, but vectors have directions. We cannot let go their direction because without direction, vector has no meaning. Now, how do I incorporate directions in these equations? We have done that before and we are going to do it again. How do I incorporate directions in this? To incorporate direction in this, in the red zone, when I say red zone, I mean the equation of motion. When I mean the red zone, I mean the equation of motion here. Oops, my red pen is not here. The equation of motion here. Now, how do I incorporate the vector sign here? To incorporate the vector sign here, I have a sign convention. So I will write everything with plus and minus. Yes, Neha, that is exactly what I was about to say. I will incorporate sign convention. For example, if the motion is taking place along x-axis, I will call one direction as positive and I will call the other direction as negative. So this is how I incorporate the direction of vectors in the equation on the right hand side or the right side. If the equation is taking place along y-axis, I will call the upside, the positive y-axis as positive, and I will call the downside as negative. The equation can take place in two dimensions, so I will make two equations, one along x-axis, one along y-axis. I will use the convention for x-axis on the x-wala equation. I will use the convention for y-axis on the y-wala equation, and I will solve the problem. Remember, equation on one axis, one dimension is independent of equation on the other axis or the other dimension. Do we understand this? Can I have some raised hand? That yes, sir. You understand the sign convention. Sign convention has to be put. Without sign convention, if I put everything as positive, the direction wala sense is gone. And once the direction wala sense goes away, things become wayward. Things become absolutely stupid. Vectors are vectors and they have directions. So you must respect their directions and never forget. That was the red side. How do I incorporate the directions here on the blue side? And we have just now seen it. Can anyone recollect how I'm going to incorporate the directions? Because apart from average angular velocity and angular displacement, large angular displacement, everything else is a vector. How do I incorporate the direction of these angular vectors? They're not angular vectors, they are actual vectors. How do I incorporate the directions in this? I'll give you a minute to give me the answers. What is the answer? How do I incorporate it? How do I get the sense of direction in this equation? How will I do it? What will I do it? How will I do it? Now remember, on the right hand side, the motion can be along x-axis and y-axis. It can be simply on x-axis, motion in one dimension. It can simply on y-axis, again motion in one dimension. It can be motion in a plane, motion in two dimension. But on the left hand side, the blue one, what we are going to do is the motion is only going to take place. And you must remember that the motion is only going to take place on one axis. So if it is x-axis, it will only be x-axis, whether plus or minus. If it is y-axis, it will be only y-axis. All these are actual vectors. So when the body is moving along positive y, it is actually rotating like this. I hope you understand this. If it is rotating on negative y, it is rotating like this. I hope you all understand this. If it is rotating on plus x, it is rotating like this. Right hand thumb rule. If it is rotating on minus x, it is rotating like this. Can you tell me how will I get the direction in the blue equation? I've already discussed that many a times. Can anyone tell me how do I discuss, how do I put the direction here? What is the sign convention here? In short, no one knows it? What is the sign convention here? We have done questions on that in the previous class. We had discussed the sign convention of angular motion in the previous class. No one recollects it. That's not a good sign. Positive x axis and positive y axis are positive. That is correct. Negative x and negative y are negative. That is correct. But Now remember, whatever questions you are going to encounter in this chapter on circular motion, the motion is not going to be along positive x and positive y, or negative x and negative y. Uh, it will be along positive z axis. The motion will be on the surface of your books. Things will be moving on the book in circular path like this. Now, when they are moving on the book and you look at x, y, and z axis, the positive z axis always comes out. And then that is why I told you, if something is moving in anti-clockwise sense, it would be taken as positive, and if something is moving in the clockwise sense, it is taken as negative. This anti-clockwise, why anti-clockwise is taken as positive? The answer is very simple. According to simple sign convention, simple positive x, positive y, and positive z. This positive z axis comes out of the board of your paper, and therefore this anti-clockwise is taken as positive, and this clockwise basically represents minus z axis. This clockwise represents minus z axis, and therefore it is taken as negative. So if something is moving in the anti-clockwise sense, we will take it as positive, whether it is angular velocity, whether it is angular displacement, whether it is angular acceleration, we will take it as positive. Something on the clockwise sense will be taken as negative. Do we all understand this? Can I have some reason that we understand this? I will give you a minute to note down this concept. Let us move further, and before winding off this class, just see one concept that makes things clear. And here I have shown in the sheet a rotation which is taking along positive y-axis. As you can see, this axis, oops, this axis is your positive y-axis. If something is moving along positive y-axis, this direction will be taken as positive. Are you getting my point? If it is rotating like this direction is positive. If omega is like this, omega is positive. If alpha is like this, it is positive. Do we understand this? Can I have some reason that we understand this? This would be positive, and if it rotates on minus y axis, so minus y axis would be here. Now if you look at this rotation of minus y axis, this rotation would go like this. This rotation would go like this, and when this rotation goes like this, that would be taken as negative. Is it clear to everyone in the class about positive and negative sense of rotation in circular motion or in rotation? That is how I'm going to end this class today. In today's class, we have seen the equation of motion for constant angular acceleration, which are exactly similar to the equations that we had seen in motion in 1D. We have also seen the sign convention positive and negative. And remember, here things will only rotate or move on one axis only. On that particular note, I will end up the class today, and we'll meet in the next class. I hope you have a good day. You stay safe at home, stay happy, stay healthy, take care. The class is dismissed. Bye bye.